A galaxy the size of the Milky Way, packed with hundreds of billions of stars, fully formed 13 billion years ago. The universe was only 300 million years old. Scientists stared at James Webb's data and checked it again and again. The math said impossible. The image said otherwise. We are going inside 33 discoveries that are quietly breaking cosmology open, from galaxies that outgrew the laws of physics, to black holes that appeared before anything should have been there to feed them, to a universe that may have started differently than every textbook ever printed. If you enjoy the journey, subscribe and drop a like. It keeps us going. Get ready. We begin now. The image arrived on a Tuesday morning, and within hours, astronomers around the world were quietly panicking. James Webb Space Telescope had just released its first deep field image, a single photograph. A patch of sky about the size of a grain of sand held at arm's length. And inside that tiny sliver of darkness, there were thousands of galaxies, some of them ancient, some of them so ancient they had no business looking the way they looked. Scientists expected to see faint, smudgy blobs. The early universe, according to decades of theory, should have been full of small, chaotic, half-formed structures, still figuring out how to be galaxies. Messy, primitive, young. What they saw, instead, stopped people mid-sentence. Fully shaped galaxies, bright, massive, structured, sitting at distances that placed them in the first few 100 million years of the universe's existence. Structures that, by every model ever built, should not have been possible yet. One researcher described the feeling as opening a time capsule and finding a smartphone inside. The team running the early release observations had planned for surprises. James Webb is the most powerful space telescope ever built, and surprises were expected. But the scale of what they found crossed a line from exciting into genuinely unsettling, because these galaxies didn't just slightly challenge existing models. They demolished the timeline. Here is what makes that so significant. Cosmology, the science of how the universe evolved, runs on a framework called the Lambda cold dark matter model. It took decades to build. Thousands of researchers across generations contributed to it. It has survived every major test thrown at it for over 30 years, and it has one very specific prediction about how galaxies form. Slowly, gravity pulls matter together over vast stretches of time. Small clumps merge into bigger clumps. Bigger clumps eventually ignite stars. Stars live and die and enrich the surrounding gas. Over billions of years, that process builds something resembling a galaxy. The first James Webb Deep Field image suggested that process was either wrong or running on a completely different schedule in the early universe. Within weeks, the data got worse, or better, depending on your perspective. Follow-up studies confirmed the initial readings. Multiple teams, using independent methods, arrived at the same conclusion. Several of the galaxies visible in that first image were genuinely ancient, genuinely massive, and genuinely there at a point in time when they had no right to be. 6 of them stood out immediately. Enormous structures, each one potentially containing as many stars as a fully grown modern galaxy. All of them sitting at a distance that placed their light at over 13 billion years old. The universe at that point was roughly 300 million years old. To put that in perspective, 300 million years is roughly the age of the oldest forests on Earth. The universe was, in cosmic terms, a seedling, and somehow it had already grown a forest. The word impossible kept appearing in papers. Scientists are careful with language. They prefer terms like unexpected or inconsistent with predictions. The fact that some researchers used the word impossible, even informally, tells you everything about how significant this moment was. James Webb had been in orbit for only months, and it had already found something that may rewrite the origin story of everything we see when we look up. The next question was obvious. How did these galaxies get there so fast? The answer is going to take everything we thought we understood and turn it upside down. Building a galaxy from scratch takes an almost incomprehensible amount of time under normal conditions. Start with the Big Bang. In the first few minutes, the universe produced hydrogen and helium, the two lightest elements. For roughly 400,000 years after that, the universe was so hot and so dense that light couldn't even travel through it. Everything was a glowing fog. Then, as the universe expanded and cooled, that fog cleared, hydrogen atoms settled, and for the next 200 million years, the universe went completely dark. No stars, no light, just slowly cooling gas drifting through expanding space. That period is called the Cosmic Dark Ages, and it is the starting line for galaxy formation. During those dark ages, gravity quietly got to work. Tiny variations in density, fluctuations smaller than anything visible, began pulling gas together into filaments and clumps. Imagine a very thin fog slowly being gathered by invisible hands into threads and knots. Those knots became the seeds of what would eventually be galaxies. The process is called hierarchical structure formation. Small things merge into bigger things merge into even bigger things. It is slow, grinding, and sequential. You cannot skip steps. A galaxy the size of the Milky Way, under this model, needs somewhere between 1 billion and several billion years to fully assemble. Stars need time to ignite. They need time to live out their lives, explode, and scatter heavier elements into the surrounding gas. That enriched gas then collapses into a new generation of stars, layer by layer, generation by generation. There is a minimum speed for this process, set by the laws of physics. Gravity only pulls so fast. Gas only cools at a certain rate. Stars only form when the conditions are exactly right. So when scientists build their computer models of the universe evolving from the Big Bang forward, those models consistently show that the first few 100 million years should look empty of anything large. You would see small, chaotic proto-galaxies, dim, unstable, struggling to hold themselves together. The fully formed, massive structures we see in our neighborhood today should only appear billions of years into the game. That is the theory. That is what every major simulation predicted. That is what astronomers expected James Webb to confirm when it looked back far enough. And then it looked. The galaxies it found in those early windows were massive enough and structured enough that, working backward, they would have needed to form in a window of time that the standard model says was barely enough to get the first stars lit. Scientists started calculating how fast those galaxies must have been converting gas into stars. The numbers came back extraordinary. Some of these structures were building stars at a rate hundreds of times faster than the Milky Way does today, sustained, apparently, for millions of years in a row. Under our current understanding of physics, that rate is extremely difficult to explain. Gas needs to cool before it collapses. Cooling takes time. Star formation has natural speed limits built into the process. Something in the early universe, confirmed by James Webb's observations, was breaking those speed limits. What was doing it, and how, is a question that does not yet have a clean answer. But the next discovery makes the picture even more extreme, because one specific galaxy, sitting in James Webb's data like a flashing alarm, carries the problem to a level that is almost personal. It has a nickname. Scientists call it the sparkler. The sparkler sits at a distance that places it roughly 9 billion light-years away, meaning we see it as it existed 9 billion years ago, when the universe was about 4 billion years old. At first glance, that seems early but not outrageous. 4 billion years is a long time. Then you look closer. Surrounding the sparkler are small, glowing clusters of stars called globular clusters. Every large galaxy in the modern universe has them. The Milky Way has about 150. They are ancient, compact balls of stars, each one containing hundreds of thousands to millions of stars packed tightly together. In modern galaxies, these clusters formed early in that galaxy's life and have been orbiting ever since, like frozen relics of the past. The sparkler's clusters are still forming. James Webb caught them in the act, and the analysis of those clusters revealed something stunning. Based on their chemical composition and the way their light behaves, some of those clusters are already old, meaning they formed very early in the sparkler's history, which pushes the sparkler's own origin point back to within the first couple of billion years of the universe. Possibly earlier, a team of astronomers studying the sparkler determined that it was already assembling into a mature structure at a time when our standard model says galaxy building was still in its most primitive, chaotic phase. The sparkler was not scrambling to form, it was already settling in, already organizing, already old enough to have ancient stellar clusters orbiting it. Here is the comparison that makes this land. Imagine finding a fully grown oak tree in a forest, and then cutting it open to count the rings. You expect maybe 20 rings, because the forest itself is only 20 years old. Instead, you count 300. The tree's age does not fit inside the age of the forest. That is the sparkler problem. The sparkler also revealed something else: its mass. Based on the light it emits and the behavior of its clusters, scientists estimated the sparkler at roughly 3 billion times the mass of our Sun at the time of observation. That is a mature, developed galaxy, sitting at a point in time when mature, developed galaxies were supposed to be rare to the point of impossible. This was confirmed through multiple independent analyses. The sparkler's age, its mass, its cluster population, all of it points to a galaxy that assembled faster than our models permit. And the sparkler is one galaxy. James Webb has found hundreds of candidates that raise similar questions. The sparkler just happens to be one of the clearest, most thoroughly studied examples. It has become a kind of symbol for the entire crisis James Webb has uncovered. One galaxy challenging the model could be a fluke. 100 galaxies doing the same thing is a pattern. And patterns, in science, demand explanations. The explanation is going to require understanding something fundamental first: how James Webb actually sees the past. Because the way this telescope works is stranger and more powerful than most people realize. Light travels fast, about 186,000 miles per second, which is the fastest anything in the universe can move. But the universe is enormous, and because light has a speed limit, seeing across vast distances also means seeing across vast amounts of time. When you look at the moon, you see it as it was about 1.25 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star beyond our sun, you see it as it was over 4 years ago. The farther you look, the further back in time you go. Every telescope is, in that sense, a time machine. James Webb takes this principle to its extreme. Its primary mirror stretches 21 feet across, made of 18 hexagonal gold-coated segments that fold out in space like the petals of a flower. It sits about 1 million miles from Earth, far enough to stay cold and dark and free from interference. And it is designed specifically to detect infrared light, which is where the story gets remarkable. When the universe expands, light traveling through it gets stretched. The farther light has traveled, the more it has been stretched. Light that started its journey as visible or ultraviolet light gets pulled by the expansion of space into longer and longer wavelengths, eventually shifting into the infrared range. Astronomers call this redshift. For a galaxy 13 billion light-years away, the light reaching us has been traveling and stretching for 13 billion years. By the time it arrives at James Webb's mirror, that light has shifted so far into the infrared that no ordinary optical telescope could see it at all. Hubble, as powerful as it was, could not reach back that far cleanly. Its instruments were built primarily for visible and ultraviolet light. The very earliest galaxies were effectively invisible to it. James Webb sees in infrared, meaning it sees exactly the wavelengths that ancient light shifts into after its long journey across the universe. It is like having eyes that were specifically built to read a code that every other telescope was blind to. When James Webb locks onto a patch of sky and collects light for hours, it is not just taking a photograph. It is assembling signals that left their sources when the universe was a fraction of its current age. Each photon that hits its detectors is a messenger from a time before Earth existed, before the Sun ignited, before the Milky Way finished forming. The telescope also carries instruments that analyze the spectrum of incoming light, breaking it into its components to reveal chemical information. This is how scientists can tell what elements are present inside a galaxy 13 billion light-years away. This is how they measure mass, temperature, and star formation rates across cosmic time. James Webb does not guess, it measures, and the measurements it has returned have been independently verified by multiple teams using different methods. The early galaxies it found are real, their distances are confirmed, their sizes and masses are confirmed, which makes the problem more serious, not less, because now that we know exactly what James Webb is capable of, what it found in those first looks at the early universe carries full scientific weight. And the next piece of what it found stretches believability even further. For decades, the timeline of cosmic history held up beautifully. Scientists mapped it carefully. The Big Bang happened roughly 13.8 billion years ago. The first stars lit up somewhere around 200 million years after that. The first small proto-galaxies began assembling around the same time. Primitive structures made mostly of hydrogen and helium, chaotic and faint. Over the next billion years or so, those proto-galaxies slowly merged and grew. By about 1 billion years after the Big Bang, the first recognizable galaxies were starting to appear. By about 3 billion years in, large spiral galaxies like the Milky Way were taking shape. The universe then continued assembling, merging, and organizing for the next 10 billion years to arrive at the cosmos we observe today. Every piece of that timeline was supported by evidence. Observations from Hubble, from ground-based telescopes, from radio observatories, and from decades of computer simulations all pointed to the same sequence. The universe had a schedule, and it followed it. The schedule rested on two pillars. The first was the speed of gravity. Gravity pulls matter together, but it takes time. Density fluctuations in the early universe were small. They had to grow. The growth had a rate, and that rate set the clock for everything that followed. The second pillar was the cooling of gas. Stars form inside clouds of gas, but only when that gas is cold and dense enough to collapse under its own gravity. Hot gas resists collapse. The early universe was hot. It took time to cool. Cooling set another hard limit on how fast structure could build. Between these two pillars, the timeline seemed locked in. You could not rush it. The physics would not allow it. Scientists used this framework to make predictions. If you look at galaxies from 1 billion years after the Big Bang, you should see small, irregular, low-mass systems. If you look at galaxies from 2 billion years in, you should see things slightly larger and more structured. The progression should be clear and gradual, like watching a city being built one foundation at a time. James Webb pointed at galaxies from 300 million to 700 million years after the Big Bang. The prediction was clear: expect primitive chaos. Instead, some of what it found had masses equivalent to billions or even tens of billions of times the mass of our Sunday. Already, at that age, with organized structure, with evidence of multiple generations of stars already lived and died inside them. To produce that, those galaxies would have needed to begin forming almost immediately after the universe became transparent, almost immediately after the cosmic dark ages ended. With virtually no warm-up period, the two pillars of the old timeline appear to have been either wrong, incomplete, or subject to conditions in the early universe that we have not fully identified yet. Scientists are now openly debating which explanation is least damaging to the broader framework. Ahead lies something stranger still, because some of those early galaxies are carrying a secret inside their starlight that changes the question entirely. Size should have been the easy prediction. If the early universe produced small, primitive proto-galaxies first, then the galaxies James Webb found in those earliest windows should have been small. Maybe a few percent of the Milky Way's mass. Maybe a few thousand light-years across at most. tiny, scattered, dim things doing their best to hold together against the chaos of a young cosmos. That was the expectation. It was built into every major simulation. When researchers ran their computer models forward from the Big Bang, small structures always came first. Always. James Webb found galaxies in the early universe with masses comparable to the Milky Way. Some candidates may exceed it. The Milky Way contains somewhere between 100 billion and 400 billion stars. Finding a galaxy of similar scale sitting inside the first few 100 million years of cosmic history is, by every model astronomers trusted before 2022, flatly impossible. The size problem has a technical name in the scientific literature. Researchers call it the massive galaxy problem, and it has been the subject of dozens of papers since James Webb's first data releases. Each new paper either confirms the problem or sharpens it. None of them make it disappear. Here is why size matters so much. Mass in a galaxy is mostly made of stars. Stars form from gas. For a galaxy to accumulate hundreds of billions of stars, it needs an enormous reservoir of gas and enormous amounts of time for that gas to convert into stars. The conversion rate, the fraction of gas that turns into stars per year, has physical limits. It cannot simply be cranked up to any arbitrary speed. Push it too fast, and the energy released by forming stars blows the remaining gas away before more stars can form. There is a self-regulating mechanism built into star formation that acts like a natural speed governor. To build a Milky Way mass galaxy in 300 million years, you would need to violate that speed governor. Or you would need to start with an extraordinary amount of already dense gas somehow concentrated in one place before the process even began. Or something else, something currently unknown, would need to be providing a shortcut. Scientists have proposed several candidates for what that shortcut might be. Some suggest the early universe's gas was denser and clumpier than models assumed, which would have made star formation more efficient. Some point to dark matter structures that were more concentrated early on, providing deeper gravitational wells for gas to fall into. Some suggest that magnetic fields in the early universe played a role that current models underestimate. Each of these proposals can partially explain some of what James Webb found. None of them fully explain it, and the observations keep arriving. One research group published an analysis in 2023 describing 6 galaxies that, if their mass estimates held up, would collectively contain more stellar mass than all models predicted should exist in the entire observable universe at that early epoch. 6 galaxies, more mass than the entire early universe should have had locked up in galaxies. That finding has been challenged and refined since, but the core tension remains. The early universe, confirmed by James Webb, built enormous structures faster than physics said was possible. How it managed that remains one of the most urgent open questions in all of science. And the next chapter heads directly into the engine room, where stars were forged at speeds that still make researchers uncomfortable. Inside every galaxy is a factory. Gas falls in, pressure builds, and stars ignite. The rate at which a galaxy turns gas into stars is called its star formation rate, and it is one of the most important numbers in all of cosmology. In the Milky Way today, that rate is modest. Our galaxy produces roughly 1 or 2 new stars per year. Spread across a galaxy containing hundreds of billions of stars, that is a quiet, almost sleepy pace of production. The Milky Way had most of its star-forming action billions of years ago. It has settled into a slow, steady rhythm now. Some galaxies, called starburst galaxies, form stars at dramatically higher rates, hundreds of times the Milky Way's current pace. They are spectacular objects, blazing with ultraviolet light, lit from within by the continuous birth and death of massive stars. But even starburst galaxies operate within boundaries that cosmologists understand. They are rare. They burn bright for a limited period, and they tend to appear in specific circumstances, usually when 2 galaxies are colliding and compressing each other's gas. The galaxies James Webb found in the early universe were running star formation rates that dwarf even the most extreme starburst galaxies known in the modern universe. Some of the candidates, identified in early James Webb studies, appear to have been converting gas into stars at rates of hundreds to over 1,000 solar masses per year. A solar mass is the mass of our Sunday, so these objects were building the equivalent of hundreds to thousands of sun-sized stars every single year, sustained over millions of years. To put that in physical terms, imagine a factory the size of a city that, instead of producing cars, is producing entire solar systems every single day for millions of years without stopping. That is the scale of what these early galaxies appear to have been doing. The problem is not just the rate, it is the fuel supply. At those rates of consumption, a galaxy would exhaust its gas reservoir in a geologically short time. Stars form from gas. Once the gas is gone, star formation stops. So either these early galaxies had access to an almost incomprehensible supply of gas, replenished continuously, or they ran hard and burned out fast. Some of James Webb's observations suggest the second option is closer to truth. Several of these massive early galaxies appear to have stopped forming stars entirely by the time the universe was only 1 billion years old. They lived fast, packed in their stellar mass with ferocious speed, and then went quiet. Scientists call these quenched galaxies, and finding them already quenched in the young universe is its own separate mystery. A galaxy the size of the Milky Way, fully formed and already dead by the universe's first birthday, requires explaining. The processes that quench star formation, usually energetic jets from a central black hole blasting gas out of the galaxy, take time to develop. Finding a galaxy already quenched so early suggests those processes ran faster and harder in the early universe than anything in our current models predicted. The star factories ran at impossible speeds. Then many of them shut down equally fast. The timeline makes the problem more extreme at every turn. And just beneath all of this, sitting at the center of some of these ancient galaxies, is something even more difficult to explain. Something that should have taken the entire current age of the universe to grow. In 2023, a team of astronomers released a paper that quickly spread through the scientific community. They had identified 6 objects in James Webb data that they informally called red monster galaxies. The name came from their appearance in infrared light, which showed up as intensely red signals, and from the sheer scale of what they seemed to contain. These 6 objects sat at distances placing them in the first 700 million years of the universe's history. Based on their brightness and spectral signatures, the team estimated that each one contained a mass of stars comparable to the Milky Way. One candidate may have been more massive. To understand why this sent a wave through cosmology, consider the numbers alongside each other. The universe at 700 million years old contained a total amount of matter that had been set at the Big Bang. That matter was distributed across space according to well-understood physics. The fraction of that matter that could realistically have collapsed into stars by that point in time, given all the speed limits built into the process, was calculated and agreed upon by virtually all models. It was a small fraction. The 6 red monster galaxies, taken together, appeared to contain more stellar mass than that fraction allowed. Combined, as if someone had taken the universe's early star budget and spent most of it in just 6 places. The paper was peer-reviewed. The team was careful. They included uncertainties, flagged assumptions, and called for follow-up observations. But even in the most conservative interpretation of their findings, the galaxies were deeply problematic for standard models. Follow-up observations came quickly. Some of the initial mass estimates were revised slightly downward as better spectroscopic data came in. But the fundamental problem survived the revision. These galaxies were too massive, too early, by a margin that could not be explained away by measurement uncertainty alone. One comparison from that period became widely cited. Astronomers noted that finding these galaxies in the early universe was roughly equivalent to arriving at an archaeological dig of a city that supposedly burned down 1,000 years ago and finding skyscrapers still standing. The architecture does not match the timeline. The construction speed implied is impossible by known methods. What made the red monster galaxies especially difficult was their color, or more precisely, what caused their redness. In the infrared, very old stellar populations look red, So do dusty galaxies where young stars are heavily obscured. Separating these two explanations required careful spectral analysis, and in several cases, the data pointed toward old stellar populations, meaning the redness came from stars that had already been forming and aging for hundreds of millions of years inside galaxies that the universe was supposedly too young to have built. Old stars, inside young galaxies, inside a young universe. Every layer of that sentence is a problem. The red monster galaxies became a rallying point for cosmologists who had already been quietly worried that James Webb would reveal exactly this kind of crisis. The worry turned out to be justified, and the framework that was supposed to hold all of this together, the cold, dark matter model, was about to face its most direct and uncomfortable challenge yet. Counting stars is how astronomers measure a galaxy's age and history. Every star in a galaxy represents a chapter in that galaxy's story, a moment when gas collapsed and ignited, when nuclear fire lit up for the first time. When you look at a galaxy and measure how many stars it contains, you are reading its biography. The early galaxies that James Webb found had already written too many chapters. Here is the specific problem. Stars form from gas. Gas collapses when it is dense and cold enough. When a star ignites, it releases enormous amounts of energy into the surrounding gas, heating it and slowing further collapse. This creates a natural rhythm to star formation, bursts of activity, followed by cooling periods, followed by more bursts. The cycle has a pace. Over millions and billions of years, that pace accumulates into a total star count. Scientists can calculate, given the amount of gas available in the early universe and the physical limits on star formation efficiency, roughly how many stars a galaxy should contain at any given age. The calculation is not a guess. It is grounded in thermodynamics, fluid dynamics, and stellar physics, areas of science that are extremely well tested. For a galaxy to contain as many stars as the Milky Way at an age of 300 million years, it would need to have been forming stars at a rate so extreme that, in the language of the models, it is sometimes described as physically implausible under standard conditions. Think of it this way. Suppose you could build a house by stacking one brick per second, and someone handed you a completed 50-story skyscraper and said you had 10 minutes to build it. The math simply does not work. The star count in these early galaxies is that kind of impossibility. James Webb confirmed this across multiple targets. The spectroscopic data, the detailed breakdown of light into its component wavelengths, showed stellar populations that were both numerous and, in some cases, already old, meaning the galaxies had not only formed enormous numbers of stars early on, they had done it early enough that some of those stars had already aged significantly by the time James Webb was capturing their light. One of the more striking confirmed findings came from a galaxy observed at roughly 400 million years after the Big Bang. Analysis of its starlight indicated that the most recent burst of star formation in that galaxy had already been declining for tens of millions of years by the time that light left the galaxy. So the peak of its star formation had occurred even earlier, pushing the origin point of its stellar population back toward a window so close to the Big Bang that gas clouds should still have been too warm and diffused to collapse at all. Every observation adds more entries into a log that keeps saying the same thing. The universe built stars faster, earlier, and in greater numbers than any model running before James Webb's launch had predicted. And the deeper James Webb looks, the clearer it becomes that this is a systemic issue. The problem is everywhere in the early universe, and it demands a rethinking of something that has been fundamental to cosmology for decades. What that something is, and why it matters for every living thing on this planet, is where things are about to take a sharp and unexpected turn. The speed limit on star formation is real. It comes from physics, and it is not arbitrary. When gas in a galaxy begins to collapse under gravity, it heats up. Hot gas pushes outward. For the collapse to continue and eventually form a star, the gas needs to radiate that heat away fast enough to stay cool. This cooling process takes time, and it sets a ceiling on how quickly stars can form in any given region of space. There is also stellar feedback. When massive stars form, they blast out ultraviolet radiation, stellar winds, and eventually supernova explosions. All of that energy heats and disperses the surrounding gas, which slows or stops new star formation in the same area. This feedback is like a fire suppression system built into the galaxy itself. It prevents runaway star formation from simply converting all available gas into stars at once. Because of these two mechanisms, cooling limits and stellar feedback, the maximum rate at which a galaxy can form stars is bounded. Astronomers call the theoretical ceiling the Eddington limit for star formation, borrowing the concept from accretion physics. A galaxy forming stars at or near this limit is doing the absolute most that physics permits. Some of the early galaxies James Webb identified appear to have been operating at or beyond this limit. One study published in 2023 examined a galaxy confirmed to exist at roughly 500 million years after the Big Bang. Its star formation rate, derived from the intensity and spectrum of its ultraviolet and infrared emissions, came back at approximately 1,000 solar masses per year. That is 1,000 stars the size of our Sun being born every single year, sustained, in a galaxy that should barely have had time to accumulate its gas supply. For context, the Milky Way at its most active, several billion years ago, during its peak star-forming era, reached rates of perhaps 10 to 20 solar masses per year. The number 1,000, in a galaxy that young, sits in territory that standard models simply do not reach. Researchers have proposed several ways to explain this. One possibility is that the interstellar gas in the early universe was denser and more concentrated than our models assume, which would have made cooling faster and star formation more efficient. Another possibility involves the temperature of the cosmic microwave background radiation, which was significantly warmer in the early universe and may have interacted with gas in ways that accelerated certain processes. A third possibility, more radical and gaining traction, is that some early galaxies had access to a continuous supply of cold gas flowing in along cosmic filaments, dense threads of dark matter and gas that crisscross the universe. If cold gas streamed into these galaxies continuously, replenishing what was converted into stars, the formation rate could have stayed extraordinarily high for longer than isolated systems would allow. All three of these mechanisms are theoretically possible. None of them alone explains what James Webb is observing. Combinations might help, but the numbers are still stubbornly extreme. Something in the early universe allowed star formation to operate at speeds our models have never accommodated. And woven through all of this, invisibly, is a substance that fills the universe but has never been directly detected. A substance whose behavior in the early universe may hold the key to all of it. You cannot see dark matter. You cannot touch it, photograph it, or detect it with any instrument currently built. It emits no light, absorbs no light, and interacts with ordinary matter almost exclusively through gravity. And yet, it makes up roughly 85% of all the matter in the universe. Scientists are confident it exists because of what it does. Galaxies rotate in ways that ordinary matter cannot explain without a vast, invisible scaffolding surrounding them. Light bends around galaxy clusters in ways that require far more mass than the visible matter provides. The large-scale structure of the universe, its web of filaments and voids and clusters, matches simulations only when dark matter is included. Remove it from the equations and the universe falls apart. Literally, galaxies would fly apart and cosmic structure would never have formed at all. Dark matter is the skeleton around which ordinary matter drapes itself to build galaxies. That much is confirmed. So where does it fail? The standard picture of dark matter, called cold dark matter, describes it as made of slow-moving particles that clump together gradually under gravity. Cold means they are slow relative to the speed of light. This slowness is important because it governs how early and how efficiently dark matter forms concentrated clumps called halos. These halos are the birthplaces of galaxies. Gas falls into a dark matter halo, cools, and forms stars. The halo's mass determines how much gas it can hold and how massive the eventual galaxy can become. In cold, dark matter models, the first halos are small. They form early, but remain low mass for a long time. As the universe ages, they merge into progressively larger halos, eventually hosting progressively larger galaxies. This is the foundation of the hierarchical structure formation model, and it is the direct reason why the standard timeline predicts small, primitive, early galaxies. James Webb's findings challenge this foundation. For the galaxies James Webb found to exist at 300 to 700 million years after the Big Bang, at the masses they appear to have, the dark matter halos hosting them would need to have been extraordinarily large, extraordinarily early. The cold dark matter model struggles to produce halos of that mass at that time. Simulations fall short. The gap between what the model predicts and what James Webb observes is measurable, consistent, and growing with each new data release. Some researchers have proposed that dark matter might be warmer than the cold dark matter model assumes. Warmer dark matter particles move faster, which changes how clumps form. Others have proposed that dark matter interacts with itself in ways not currently modeled, allowing it to concentrate differently in the early universe. These ideas are theoretical, unconfirmed, and represent a significant departure from the standard framework. A few researchers have gone further. They have asked whether dark matter behaves according to entirely different rules in the early universe, rules that shift as the cosmos evolves. That idea remains highly speculative. What is confirmed is this: the cold dark matter model, in its standard form, does not comfortably produce the structures James Webb has found in the early universe. Adjustments are needed. How large those adjustments must be is still being determined. And those adjustments may become even more extreme when you consider the framework those models are embedded in, a framework that has ruled cosmology for 3 decades and is now facing the most serious questions of its existence. Lambda cold dark matter. That is the full name of the framework that describes how the universe evolved from the Big Bang to today. Lambda refers to the cosmological constant, the term Einstein added to his equations to account for the energy driving the universe's accelerating expansion. Cold dark matter describes the dominant form of matter shaping cosmic structure. Together, they form a model so successful that for 30 years, no observation could crack it. James Webb is cracking it. The model makes specific, testable predictions about the early universe, the number of massive galaxies at different cosmic ages, the star formation rates across time, the distribution of galaxy sizes in any given era. These predictions are not vague. They are precise enough to compare directly against observations. Early James Webb data, confirmed across multiple independent teams, shows a statistically significant excess of massive, bright galaxies in the early universe compared to what lambda cold dark matter predicts. The excess is not slight. In some mass ranges and redshift windows, the observed number of galaxies is several times higher than the model's predictions. Several times. That is far outside the margin of error. Scientists have options when a model faces observational pressure. The first option is to refine observations and check for systematic errors. That has been done, repeatedly, by different groups with different methods. The discrepancy persists. The second option is to adjust the model's parameters, tweak inputs like the efficiency of star formation or the behavior of supernova feedback. Teams have tried this too. Adjustments help at the margins, but cannot close the full gap. The third option is to consider whether something fundamental in the model requires revision. That third conversation is now happening in the open. Papers have appeared in major journals questioning whether cold dark matter is truly cold, whether the cosmological constant is truly constant, whether the initial conditions of the universe, the specific pattern of density fluctuations seeded by the Big Bang, were different from what the model assumes, whether some new physics, operating in the first billion years and then switching off or fading, could explain what James Webb sees. None of these proposals have been proven. All of them represent serious science done by credentialed researchers at major institutions. The fact that multiple competing explanations are on the table simultaneously tells you something important. The answer is genuinely unknown. What is known is that the lambda cold dark matter model, in its standard unmodified form, does not reproduce the early universe that James Webb has photographed and measured. Something is off. The question of exactly what is off will likely define cosmology for the next decade. The universe apparently did not follow the script written for it. And somewhere inside that failure, there may be an entirely different explanation for how everything began. One that reaches back before the galaxies, before the stars, before the first atoms, to a moment so extreme that our current physics breaks down entirely. Every cosmological model starts at the same place, the Big Bang. The moment, approximately 13.8 billion years ago, when the universe as we know it began expanding from an extraordinarily hot, dense state. Everything since then, every galaxy, every star, every atom in your body, traces back to conditions in those first moments. The initial conditions of the Big Bang are not perfectly understood. What we know comes primarily from the cosmic microwave background radiation, the faint glow of heat left over from the early universe, detected and mapped by satellite missions with extraordinary precision. That map reveals tiny temperature fluctuations across the sky, fluctuations that directly reflect the density variations in the early universe. Those density variations were the seeds of all structure. Galaxies formed where matter was slightly more concentrated. Voids opened up where it was slightly less. The pattern of those fluctuations fits the lambda cold dark matter model remarkably well. This is one of the model's greatest triumphs. It predicted the statistical pattern of the cosmic microwave background before it was fully mapped and the map matched. That success built enormous confidence in the model. Now, James Webb is showing that something happened between that early pattern of fluctuations and the galaxies that actually formed. The galaxies are too big, too massive, too early. Something amplified the process of galaxy formation beyond what the seed fluctuations, combined with known physics, should allow. One possibility being actively studied is that the Big Bang itself was preceded or accompanied by a phase called inflation, a period of extremely rapid expansion that stretched and smoothed the early universe. Inflation is confirmed as a concept by the large-scale structure we observe, but the details of inflation, exactly how it happened, for how long, and what caused it to end, remain deeply uncertain. Different inflation models produce slightly different patterns of initial fluctuations. Some models of inflation produce initial conditions that are more favorable to rapid early galaxy formation than others. Researchers are now working backward from James Webb's observations to ask, what initial conditions would have been needed to produce the early universe we are seeing? The answer points toward something different from the standard assumption. Slightly more power on small scales in the initial fluctuation pattern, slightly clumpier starting conditions. Whether that difference is large enough to require a fundamental revision of inflation theory or simply a refinement within existing models is currently unclear. But the fact that researchers are re-examining the Big Bang's initial conditions in response to what a telescope found is itself remarkable. James Webb is not just observing the distant universe, it is constraining what happened in the first fraction of a second. And lurking alongside this question, so strange and extreme that for years it was considered too speculative to take seriously, is an idea about what might have seeded those earliest galaxies. An idea involving objects that may have formed before the first stars, before the first atoms, in the universe's most violent opening moments. Black holes are supposed to form when massive stars die. A star many times heavier than our Sun exhausts its fuel, collapses under its own gravity, and if it is massive enough, nothing stops that collapse. It continues until the star vanishes behind an event horizon, a boundary from which even light cannot escape. The black hole is born from stellar death. That is the standard process. It requires stars to exist first. Stars require time to form. Time requires the universe to have already progressed through the Dark Ages, through the first generation of gas collapse, through ignition. By this sequence, black holes cannot predate the stars that create them. Primordial black holes break that sequence entirely. The theory of primordial black holes proposes that in the first fractions of a second after the Big Bang, when the universe was extraordinarily dense and chaotic, regions of space with slightly higher density could have collapsed directly into black holes without ever forming stars first. The conditions needed for this require density fluctuations larger than what standard inflation models typically produce. But some inflation models do allow it, and the idea was mostly a theoretical curiosity for decades because there was no observational evidence requiring it. James Webb may be changing that. Here is the connection. One of the most persistent mysteries in the early universe data is the presence of supermassive black holes, objects containing millions or billions of times the mass of our Sun, already sitting at the centers of early galaxies. These objects require explanation because growing a black hole to supermassive scale through normal stellar feeding takes an enormous amount of time. Yet James Webb finds them operating, lighting up their host galaxies, at cosmic ages of only a few 100 million years. If primordial black holes formed in the Big Bang's first moments, they would have had a head start. They would already exist when gas began to cool and collect. Gas falling onto a primordial black hole would form a disk, heat up, and radiate intensely, creating the bright central engines called quasars that James Webb has detected at extraordinary distances. The black hole, already large at birth, would grow faster than any black hole formed from stellar death could. Additionally, a primordial black hole sitting in the early universe would act as a gravitational anchor. Gas would preferentially fall toward it. A galaxy would begin assembling around it faster than it would around a simple dark matter halo with no central concentration. This could, in principle, explain both the massive early galaxies and the supermassive black holes inside them. Two problems, one mechanism. Primordial black holes remain a theory. They are confirmed as a concept by general relativity, but their actual existence in the early universe has not been proven. However, the number of researchers taking them seriously has risen measurably since James Webb's early releases. They fit the observational picture better than several more conventional explanations. And the galaxies James Webb finds are not just large and early. Some of them have already done something else that amplifies the problem to its next level, something that speaks to a kind of cosmic premature aging that, when you understand what it implies, makes the timeline feel stranger than it has at any point so far. The universe, in its youth, should have been bursting with activity, star formation blazing, gas cycling, galaxies churning. The early cosmos should have been the most energetically productive era in all of cosmic history, a furnace running at full intensity. Some galaxies James Webb found in those earliest windows had already gone quiet. Astronomers call these objects quenched galaxies. They have stopped forming stars. Their gas has been exhausted, ejected, or heated to a state where it can no longer collapse. The stars that exist inside them are the stars that formed during an earlier active phase. New stars are no longer being added. The galaxy is, in a sense, finished. It will slowly dim over billions of years as its existing stars age and die without replacement. Finding quenched galaxies in the modern universe is common. The Milky Way's neighborhood contains many of them, large elliptical galaxies filled with old red stars, no longer actively forming new ones. They quenched billions of years ago after their star-forming era ended naturally. That process, from active formation to quenching, took several billion years in most cases. James Webb found galaxies that had already quenched within the first billion years of the universe. One confirmed example sits at a distance, placing it at roughly 700 million years after the Big Bang. Analysis of its light showed a stellar population dominated by old, red stars, the signature of a galaxy whose star formation had ended. No significant ultraviolet emission, which would indicate young, hot stars. No detectable ongoing star formation. A galaxy already retired, in a universe still in its infancy. The problem is the timeline of quenching. For a galaxy to quench, something must strip away or heat its gas supply. The main mechanisms known to do this in the modern universe involve energetic jets from supermassive black holes blasting gas out of the galaxy, or the gravitational effects of galaxy cluster environments. Both of these mechanisms take time to develop and operate. A galaxy quenching at 700 million years after the Big Bang would have needed to form rapidly, accumulate stellar mass at extreme rates, trigger its central black hole into a violently energetic state, have that black hole expel the remaining gas, and then go quiet, all within less time than it took Earth's oceans to form after the planet solidified. The condensed timeline is not just surprising, it implies that every stage of galaxy, evolution, formation, peak activity, black hole activation, and quenching can run far faster than our models predict. If the fast version of the cycle was common in the early universe, the standard model's timeline requires significant revision across all of its phases, not just the formation stage, and quenched early galaxies reveals something else when you look at their size. These dead galaxies in the early universe are compact, much smaller than quenched galaxies of similar mass in the modern universe. Same stellar mass, dramatically smaller volume, which means the stars inside them are packed together at densities that dwarf anything we see in nearby quenched galaxies. How those ultra-compact dead galaxies eventually grew into the large, diffuse, elliptical galaxies we see today is yet another unsolved problem layered onto the pile. And at the bottom of that pile sits one of the most disorienting paradoxes in all of cosmology. Cosmology predicted that small things come first. Small, dark matter halos, small proto-galaxies, small star clusters. Over time, through mergers and accretion, these small things grow into larger things. The biggest structures in the universe, the massive elliptical galaxies, anchoring large galaxy clusters, should be the youngest, the last to fully assemble. The observations say the opposite. This is called the galaxy downsizing paradox, and it has been a problem in cosmology since before James Webb. But James Webb has made it sharper, more concrete, and harder to dismiss. The paradox works like this. When astronomers survey galaxies across different cosmic ages, they find that the most massive galaxies, the giants, completed their star formation earliest. They built up their stellar mass fast in the early universe, then stopped. Smaller galaxies, galaxies like the Milky Way, continued forming stars for much longer and are still forming them today. The biggest formed first and fastest. The smallest are still building. This is directly inverted from the hierarchical model's prediction. Hierarchical assembly says the largest structures take the longest to assemble because they require the most mergers, the most time for gravity to pull enough material together. But the observed universe shows the most massive galaxies finishing their construction earliest. Several explanations have been proposed. One centers on the efficiency of star formation in high-mass dark matter halos. If the most massive halos formed early enough and concentrated their gas efficiently, they could have built massive galaxies quickly. The problem is producing those massive halos early enough, which brings us back to the cold dark matter problem from Chapter 11. Another explanation involves the relationship between a galaxy's mass and its central black hole. More massive galaxies host more massive central black holes. More massive black holes can produce more powerful jets, which quench star formation more efficiently. So the largest galaxies may have self-terminated their star formation fastest, explaining why they appear done while smaller galaxies continue building. The evidence for this mechanism exists, but it requires the central black holes to have grown to enormous mass very quickly, which is itself a separate problem. James Webb has deepened the paradox by finding massive quenched galaxies at earlier cosmic times than previous telescopes could probe. Each new confirmed example of a massive, already dead galaxy at high redshift tightens the constraint on any model trying to explain downsizing. The paradox matters beyond its immediate scientific implications. It tells us that our intuition about how the universe builds things from small to large, bottom to top, is at minimum incomplete and possibly fundamentally wrong in ways that cascade through all of cosmology. If the biggest structures formed first, then the universe did something in its early phases that our physics has not fully captured. Something that concentrated power early, built fast, and then let things slow down, identifying that something is now one of the central targets of observational cosmology. James Webb, by looking further back than any instrument before it, has made that target visible for the first time. And understanding how the telescope actually achieves that view, how its engineering translates into cosmic discovery, will reveal why no other instrument in history could have shown us any of this. James Webb did not just improve on what came before, it opened a window that was previously sealed shut. Every telescope operates within a range of light. The human eye sees visible light, a narrow band in the electromagnetic spectrum. Hubble was built to excel in visible and ultraviolet light. It could reach into near-infrared, but only partially, and with limitations that became critically important when looking at the most distant objects in the universe. The problem is redshift. Light stretches as the universe expands. The farther a galaxy sits from us, the faster the space between us, and it is expanding, and the more its light gets stretched toward longer wavelengths. Visible light shifts to red light shifts to infrared shifts to far infrared. For objects at the extreme distances James Webb targets, galaxies in the first few 100 million years of the universe, essentially all of the light has been stretched out of the visible range entirely. Those galaxies are infrared objects. Looking for them with a visible light telescope is like trying to read a page with a flashlight pointed in the wrong direction. James Webb was designed around this fact from its earliest conception. Its primary mirror, 21 feet across, is made of beryllium, a metal light enough to be launched into space, but stiff enough to maintain the precise shape needed for accurate focusing. Each of its 18 segments is coated in a layer of gold just a few millionths of an inch thick. Gold reflects infrared light more efficiently than any other practical coating. The mirror is engineered to collect infrared light with sensitivity that no previous space instrument approached. The telescope also carries a sunshield the size of a tennis court, a 5-layer membrane that keeps the mirror and instruments in permanent shadow. Cold is essential for infrared detection. Heat generates infrared radiation. If James Webb's instruments were warm, they would be blinded by their own thermal glow. The sunshield keeps the telescope's instruments cooled to about minus 447 degrees Fahrenheit, close to absolute zero, allowing them to detect the faintest infrared signals arriving from across the universe. James Webb's instruments include spectrographs, devices that take incoming light and spread it into its component wavelengths like a prism spreading sunlight into a rainbow. By analyzing the specific pattern of wavelengths in a galaxy's light, scientists can determine what elements are present, how fast stars are forming, the age of the stellar population, the mass of the central black hole, and the galaxy's distance with precision. The spectrum is a complete dossier on an object billions of light years away. Hubble gave us a universe of blurry, faint smudges at extreme distances. James Webb gives us detailed portraits, the same patches of sky that Hubble photographed over days of exposure, showing faint candidate objects. James Webb resolves into confirmed galaxies with measured distances and detailed physical properties. This is why the discoveries of the past few years carry such weight. Earlier telescopes found hints and candidates. James Webb delivers confirmations. The massive early galaxies in its data are measured objects with real spectra and real distances, verified independently. The crisis they represent is not based on interpretation of ambiguous data. It is based on precise measurement, and the most precise measurements James Webb is now taking are about to reveal something inside those ancient galaxies that deepens the mystery far beyond size and star counts. Something chemical, something that carries the fingerprints of a universe operating by rules we have not yet fully decoded. Hubble launched in 1990, and it transformed astronomy. For over 3 decades, It gave humanity its deepest views of the cosmos. Its ultra-deep field images, exposures lasting nearly 1 million seconds, accumulated over many sessions, showed thousands of galaxies packed into a patch of sky smaller than a grain of sand. Those images became iconic. They became proof of the universe's vastness and age. But Hubble had a ceiling. At the extreme distances corresponding to the universe's first billion years, Hubble's sensitivity fell off sharply. Objects that far away had their light stretched so far into infrared that Hubble's detectors, optimized for visible and ultraviolet wavelengths, caught only fragments, faint smudges, candidate objects that required statistical arguments to interpret. Researchers could identify promising targets at those distances, but confirming their nature, measuring their spectra, determining their true masses and star formation rates was often impossible. So, cosmologists built their models of the early universe based on extrapolation. They took what Hubble showed clearly in the first few billion years and projected backward, using theory to fill the gap where observation was thin. The early universe, in those models, looked primitive, not because Hubble showed it to be primitive, but because the models said it should be, and Hubble could not see well enough to contradict them. James Webb pointed at Hubble's most famous deep field patches, the same coordinates, the same regions of sky that Hubble had photographed over decades. And in a fraction of the exposure time, James Webb revealed a completely different universe hiding in those same pixels. Objects that appeared as faint, ambiguous smudges in Hubble images resolved into structured galaxies with clear morphology. Candidates that Hubble flagged as possibly very distant turned out to be confirmed. Spectroscopically verified galaxies sitting at distances Hubble could barely reach. And in the spaces between Hubble's known objects, James Webb found entirely new galaxies that had been invisible before, ancient and massive, hiding in wavelengths Hubble's instruments could not detect. One comparison became a defining image of the early James Webb era. Side by side, Hubble and James Webb photographs of the same region, where Hubble showed a relatively sparse field with a scattering of known galaxies, James Webb showed a dense tapestry of structure, with resolved shapes, colors indicating stellar populations, and background objects stretching to distances Hubble had never cleanly reached. The difference was not a matter of resolution alone. Though James Webb's resolution is extraordinary, the fundamental difference was wavelength access. Hubble was built for one range of light. James Webb was built for the range that ancient light actually occupies after billions of years of cosmic expansion. Hubble was reading the universe in a language that ancient galaxies no longer speak. James Webb learned the language they actually use. This means that every conclusion cosmologists drew about the early universe based on Hubble's deep fields was based on incomplete data. The models were constrained by what Hubble could see, and Hubble could not see the full picture. James Webb is not merely improving on Hubble, it is correcting a systematic blind spot that existed across 30 years of deep field astronomy. The implications reach beyond the specific discoveries. Every time a new telescope has opened a genuinely new window on the universe has surprised us. Radio telescopes revealed quasars. X-ray telescopes revealed a violent, energetic cosmos invisible to optical instruments. James Webb is doing the same for the infrared universe, and the surprises are arriving faster than most researchers anticipated. Each one of those surprises carries a number, and hidden inside those numbers is a tool called Redshift that tells us exactly how far back in time we are looking, with a precision that makes everything James Webb has found impossible to dismiss. Redshift is one of the most powerful tools in all of astronomy. It is also beautifully simple in concept. When a source of light moves away from you, the waves of light it emits get stretched. The same thing happens with sound. When a car drives away, the pitch of its engine drops, because the sound waves are being stretched by the increasing distance. Light behaves the same way. As a distant galaxy moves away from us, carried by the expansion of space, the light it emits gets stretched toward longer, redder wavelengths. The faster the recession, the greater the stretch, the higher the redshift. And because the universe is expanding uniformly, a galaxy's recession speed is directly tied to its distance. Farther galaxies recede faster. More redshift means greater distance. Greater distance means we are seeing the galaxy as it was longer ago. Redshift, distance, and look-back time are all linked in a chain that cosmologists can follow precisely. Measuring redshift requires a spectrograph. You spread a galaxy's light into its component wavelengths. You look for known patterns, specific wavelengths emitted or absorbed by known elements like hydrogen, oxygen, and carbon. Those patterns act as fingerprints. In a nearby galaxy, those fingerprints sit at their standard positions. In a distant galaxy, the whole pattern has shifted toward the red end. By measuring how far the pattern has shifted, you calculate the redshift. From redshift, you calculate distance and look-back time. James Webb's spectrographs perform this measurement with extraordinary sensitivity. They can detect the spectral fingerprints of elements in galaxies so distant that their light left when the universe was only a few % of its current age. Every galaxy that James Webb spectroscopically confirms at extreme distance carries a redshift measurement that is not an estimate or an inference. It is a direct measurement of how much the universe expanded while that light was traveling. The highest confirmed redshifts James Webb has measured correspond to galaxies seen as they were roughly 200 to 300 million years after the Big Bang. The universe at that point was less than 2% of its current age. Light from those galaxies has been traveling toward us for over 13 billion years. Redshift also reveals something additional. The chemical fingerprints in a galaxy's spectrum tell you which elements are present. Hydrogen is universal, but heavier elements like carbon, oxygen, silicon, and iron are forged inside stars and scattered when those stars die. A galaxy rich in heavy elements has already cycled through at least one generation of stellar birth, life, and death. When James Webb detects carbon and oxygen in galaxies at extreme redshifts, it is finding chemical evidence of stellar generations that lived and died before the universe was 1 billion years old. That chemical evidence is independent of mass estimates and size measurements. It is a completely separate line of confirmation that something was happening in the early universe at speeds our models were not built to accommodate. Redshift is also at the heart of one of the deepest tensions in modern cosmology, a conflict that James Webb did not create but has significantly sharpened. Two independent methods of measuring the universe's expansion rate give two different answers. Both are carefully done. Both have been checked repeatedly. They disagree, and the implications of that disagreement reach all the way back to the Big Bang itself. That tension is about to surface fully, and when it does, the question it raises about the fundamental geometry of the universe is one that even the most careful cosmologists admit they do not yet know how to resolve. Individual galaxies forming too early is one level of problem. A fully assembled cluster of galaxies forming too early is another level entirely. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds to thousands of individual galaxies, along with enormous reservoirs of hot gas and vast amounts of dark matter, all held together by gravity into a single coherent system. The Milky Way belongs to a modest group called the local group. True galaxy clusters, like the Virgo cluster or the Coma cluster in our cosmic neighborhood, contain thousands of galaxies spread across tens of millions of light years. Building a structure like that requires time on a scale that dwarfs even galaxy formation. First, individual galaxies must form. Then those galaxies must find each other through gravity. Then they must fall together over hundreds of millions to billions of years, accumulating mass, heating gas, and slowly reaching the density needed for cluster status. Galaxy clusters are, by definition, late arrivals in cosmic history. James Webb found evidence of a protocluster, a system of galaxies already gravitationally associated and beginning to coalesce at a distance, placing it at less than 800 million years after the Big Bang. A protocluster at that age is not simply unexpected. It requires that a large number of galaxies, independently formed in the same region of space, within an extraordinarily compressed window of time, and then began interacting gravitationally before the universe had given them the time our models say they needed. The detection involved identifying a concentration of galaxies at the same redshift, meaning they all sit at the same distance and are therefore genuinely co-located in space and time rather than appearing close together by coincidence along our line of sight. Spectroscopic confirmation showed multiple galaxies within the structure already containing mature stellar populations and, in some cases, already showing signs of reduced star formation due to their environment. Galaxy clusters heat their intergalactic gas through gravitational compression and the energetic activity of member galaxies. That hot gas is detectable through X-ray emission and through its effect on background radiation. Finding a concentration already showing environmental effects on member galaxies at less than 800 million years after the Big Bang means cluster-scale processes were already operating, at a point when the standard model barely allows individual massive galaxies to exist. The finding also matters for what it implies about the seeds of structure. Clusters form in the densest regions of the cosmic web, places where dark matter filaments intersect, and matter has been accumulating longest. Finding a protocluster so early means those intersections were already extraordinarily dense within the universe's first billion years. The initial conditions must have been clumpier than standard models assume, concentrated in ways that allowed overdense regions to race ahead of the average evolution of the cosmos. Every layer of structure James Webb finds early, individual galaxies, clustered galaxies, protoclusters, adds to a coherent picture of an early universe that was more organized, more active, and more advanced than the models built before its launch had accounted for. And the deepest layer of that picture, one that touches chemistry and the origin of the atoms your body is built from, is where the story takes its most personal and unexpected turn. Every atom in your body, heavier than hydrogen, was forged inside a star. The hydrogen that makes up most of the water in your cells came from the Big Bang. Everything else, the carbon in your DNA, the oxygen you breathe, the iron in your blood, was synthesized inside stellar cores over billions of years of nuclear fusion. When massive stars died in supernova explosions, they scattered those elements into the surrounding gas. That enriched gas eventually collapsed into new stars and planets. You are, in a precise and literal sense, made of material processed through multiple generations of stellar death. This process takes time. A star must form, live out its lifespan, and die before its synthesized elements enter the interstellar medium. The most massive stars, which produce the heaviest elements, live for only a few million years before exploding. But even a few million years is a significant chunk of time in the earliest universe, when the first stars may have only lit up 200 million years after the Big Bang. James Webb has detected the chemical signatures of carbon, oxygen, nitrogen, and other heavy elements inside galaxies that existed at 300 to 500 million years after the Big Bang. For those elements to be present, stars must have already formed, completed their lives, exploded, and scattered their contents into the surrounding gas, all before the galaxies James Webb is observing had even finished assembling. The chemical evidence implies at least one full cycle of stellar birth and death before the point of observation. Some of these detections have been confirmed through multiple spectral lines, independent features in the light spectrum, each corresponding to a different element. The confirmation is not based on a single ambiguous signal. Multiple chemical fingerprints are present simultaneously, consistent with a gas and stellar population that has already been through at least one round of nuclear processing. One detection in particular drew significant attention. A galaxy at roughly 350 million years after the Big Bang showed spectral evidence of carbon and oxygen at abundances comparable to some regions of the modern Milky Way. The Milky Way is 13 billion years old and has cycled its material through stars for nearly that entire duration. Finding similar chemical abundances in a galaxy less than 4%, that age implies a rate of chemical enrichment that our models of stellar evolution struggle to accommodate. There is a proposed explanation involving the first generation of stars, called population 3 stars, which theory predicts were enormous by modern standards, possibly hundreds of times the mass of our Sun, with very short lifespans. Stars that massive would have processed gas into heavy elements and exploded as supernovae within a few million years of forming. If population 3 stars were common in the earliest galaxies, they could have enriched the surrounding gas extremely quickly. Population 3 stars have never been directly observed. Their existence is theoretical, supported by indirect evidence and stellar evolution models. James Webb is actively searching for their signatures, and some candidate detections have been reported, though none yet definitively confirmed. What is confirmed is the chemical enrichment itself. Heavy elements present too early for comfort, and sitting alongside that chemical mystery is a mechanical one that ties everything together in a way that makes the early universe feel increasingly like it was running by a different set of rules. Stars make heavy elements. When stars die, those elements are released into space. New gas clouds, now enriched with heavy elements, collapse into new stars. The process repeats. Each generation of stars enriches the next. This cycle, stretched over billions of years, is how the universe went from a cosmos of pure hydrogen and helium to one containing the full periodic table. The cycle has a starting point. The first stars formed from pure hydrogen and helium. They had no heavy elements, because no previous stars had existed to make them. Those first stars lived fast, died explosively, and seeded the first round of chemical enrichment. Then the second generation of stars formed from that slightly enriched gas, and so on. The key constraint is time. Each generation takes time. Stars must form, live, and die before the next generation can begin. The minimum timescale for this cycle, governed by the lifetimes of the most massive stars, is a few million years per generation. Running multiple generations takes tens to hundreds of millions of years. James Webb is finding galaxies at 300 to 500 million years after the Big Bang, with chemical abundances suggesting multiple generations of enrichment have already occurred. The math is tight, extremely tight. Working backward from the observed abundances and the known timescales for stellar evolution, researchers have tried to reconstruct how many enrichment cycles would have been needed to produce what James Webb detects. In several cases, the number of cycles required, multiplied by the minimum time per cycle, approaches or exceeds the age of the universe at the point of observation. A loop that should have more turns than the time allows, a cycle that began too early or ran too fast. The recycling problem has no clean solution within the standard framework. Several possibilities are being examined. One involves massive early stars, the population 3 stars mentioned in the previous chapter, whose enormous mass and short lifespans would have accelerated the first enrichment cycle dramatically. If population 3 stars were common and formed almost immediately after the cosmic dark ages ended, they could have completed an enrichment cycle within the first 50 to 100 million years. Another possibility involves the efficiency of mixing. In modern galaxies, supernova ejecta mix with the surrounding gas over millions of years. If the early universe allowed faster or more efficient mixing, perhaps due to different gas densities or magnetic field configurations, enrichment could have spread through a galaxy's gas more rapidly. A third possibility is that our measurements of these early chemical abundances are being influenced by factors not fully accounted for, such as unusual stellar populations or calibration uncertainties in James Webb spectrographs at extreme redshifts. This possibility has been examined and partially addressed, but researchers acknowledge it cannot be entirely ruled out. What cannot be dismissed is the pattern. Chemical enrichment appearing earlier than expected is consistent across multiple independent observations of different galaxies at similar distances. A pattern that persistent in confirmed data is telling us something real about the early universe. And chemical enrichment is not the only thing that appeared too early. Sitting at the centers of these chemically mature galaxies are objects that should have taken the full age of the universe to build. Objects so massive that their presence in the young cosmos represents perhaps the most extreme challenge of all to our understanding of cosmic evolution. At the center of nearly every large galaxy in the universe sits a supermassive black hole. The Milky Way has one, called Sagittarius A star, containing about 4 million times the mass of our Sunday. Other galaxies host far more massive versions. The galaxy Messier 87 contains a black hole of 6.5 billion solar masses, the one famously imaged by the Event Horizon Telescope in 2019. These are enormous objects by any measure, but growing them takes time. Black holes grow by consuming matter. Gas and dust fall in, releasing energy as they spiral down, and the black hole's mass increases. The rate at which a black hole can consume matter is limited by its own radiation output. As matter falls in, it heats up and radiates intensely. That radiation pushes back on the infalling gas. At a certain rate, called the Eddington limit, the radiation pressure exactly balances gravity, and the inflow stops. Exceed that rate, and the black hole blasts away its own food supply. Growing a black hole of several billion solar masses from a stellar remnant of perhaps a few dozen solar masses, at the maximum rate the Eddington limit allows, takes approximately 1 billion years. That is the fastest any known physical process can do it. James Webb has confirmed the existence of supermassive black holes at distances corresponding to less than 1 billion years after the Big Bang. Some candidates sit at only a few 100 million years after the Big Bang and appear to already contain masses of hundreds of millions to over 1 billion solar masses. For a black hole of 1 billion solar masses to exist at 500 million years after the Big Bang, it would need to have started growing almost immediately after the first stars formed, maintaining maximum Eddington rate feeding continuously, with no interruptions. The slightest pause in feeding would break the timeline, and continuous maximum feeding is considered extremely unlikely because stellar and supernova feedback regularly disrupts gas inflow around growing black holes. Several explanations have been proposed. The primordial black hole scenario from Chapter 14 fits naturally here. If some black holes formed directly from density fluctuations in the Big Bang rather than from stellar death, they would have begun with masses far larger than any stellar remnant, giving them a massive head start on growth. Another proposal involves direct collapse black holes. Instead of a cloud of gas-forming stars, conditions in the early universe may have allowed massive gas clouds to collapse directly into a black hole without going through the stellar phase. Theoretical models show this is possible under specific conditions involving high gas temperatures and the absence of molecules that would normally facilitate star formation. Direct collapse black holes could form with initial masses of tens of thousands to millions of solar masses, dramatically shortening the growth timeline. Both proposals remain theoretical. Neither has been directly confirmed, but the observational pressure from James Webb is pushing both ideas from the margins toward the center of serious cosmological research. What makes the early black hole problem especially compelling is its connection to everything else. The galaxies around these black holes are the same ones forming stars too fast, quenching too quickly, and showing chemical enrichment too early. The supermassive black hole problem and the galaxy formation problem are deeply entangled. Understanding one likely requires understanding the other, and that entanglement points toward a relationship between black holes and galaxies that, under early universe conditions, may have operated in a way fundamentally different from what we observe today. Black holes and their host galaxies grow together. This is one of the most robust observations in modern astronomy. Across thousands of galaxies in the nearby universe, the mass of the central black hole correlates tightly with the mass of the galaxy's central bulge. Larger galaxies have larger black holes, with a precision that suggests the two are not growing independently. They are regulating each other. The mechanism works like this. A growing black hole, fed by infalling gas, becomes an active galactic nucleus, an extraordinarily energetic engine at the galaxy's core. When feeding reaches high enough rates, The active nucleus launches jets of plasma and radiation outward through the galaxy. Those jets heat the surrounding gas, preventing it from cooling and forming new stars. Star formation slows. The galaxy begins to quench. As gas stops flowing in, the black hole's feeding rate also drops. The jets quiet down. Eventually, if gas finds its way back in, the cycle can restart. This feedback loop, black hole growth fueling outflows that suppress star formation, which in turn reduces black hole feeding, is the main mechanism cosmologists use to explain why massive galaxies stop forming stars. It also explains, at least in part, the observed relationship between black hole mass and galaxy mass. They limit each other's growth through this mutual regulation. The loop works well in the nearby universe. Observations confirm it, simulations reproduce it, but the loop requires time to operate. The black hole must grow, the jets must develop, the heating must propagate through the galaxy, the quenching must follow. Each step has a timescale. James Webb is finding galaxies in the early universe where the loop appears to have run at compressed speeds. Galaxies already quenched at less than 1 billion years after the Big Bang imply that a black hole grew, triggered powerful feedback, and shut down star formation, all within a window that is far shorter than the loop normally requires. Beyond the timing, there is a scaling problem. In the nearby universe, black hole mass is roughly a few tenths of a percent of the host galaxy's bulge mass. James Webb is finding early galaxies where the black hole appears to be a much larger fraction of the total galaxy mass. Some estimates, still being refined, suggest early black holes may have been proportionally 10 to 100 times larger relative to their host galaxy than in modern systems. If confirmed, this means the early universe ran the black hole-galaxy relationship in a different regime. Black holes dominated first. Galaxies grew around them more than alongside them. The regulation that produces the tight modern correlation may have taken billions of years to establish, starting from an early universe where black holes held disproportionate gravitational influence over young, gas-rich proto-galaxies. This inversion of the expected relationship, black hole leading galaxy rather than both growing in tandem, could explain several of James Webb's findings simultaneously. A massive early black hole provides a deep gravitational well, gas falls in faster, star formation is concentrated and accelerated near the center, feedback eventually expels remaining gas. The galaxy quenches early, compact, and at a mass set by how much star formation occurred before the black hole's feedback won out. The picture is speculative in its details, but consistent with the data. And the data, as James Webb continues operating, is beginning to hint at something even more radical, something that goes beyond adjusting the timeline and starts questioning the fundamental catalogue of objects the universe contains. Science organizes the universe into categories: galaxies, quasars, star clusters, nebulae. Each category has defining properties. Each one slots into the broader framework of cosmological evolution. The system works because the universe, despite its complexity, turns out to organize itself into recognizable types of objects that behave predictably. James Webb is finding things that do not slot. Several detections in James Webb's deep field observations have resisted clean classification. They are too compact to be resolved into individual stars, like a galaxy normally would be at their distances, but they show spectral properties inconsistent with known types of point sources. They have colors and luminosities that place them in regions of classification diagrams where no well-understood object should sit. One class of candidates has been described informally as little red dots. They appear as extremely compact, intensely red sources in James Webb images. Follow-up spectroscopy reveals broad emission lines, which normally indicate the presence of a massive, fast-accreting black hole, but their host structures, if they have host structures at all, are too faint to detect clearly. Some appear to be enormously luminous for their apparent size, suggesting either an extremely massive black hole, an extremely dense stellar system, or something combining both in proportions not seen in the modern universe. Some researchers have proposed that little red dots are a distinct phase of galaxy evolution, the moment when a young galaxy and its central black hole are simultaneously at peak activity, both growing at maximum rates before feedback quenches the system. If so, they would represent a brief, explosive transitional state that modern galaxies passed through billions of years ago, but that we can now observe directly because James Webb can see that far back. Other researchers have suggested some of these objects might be direct collapsed black holes in formation, the same objects theorized to explain early supermassive black holes. Caught in the act of assembling, if a massive gas cloud is collapsing directly into a black hole rather than fragmenting into stars, the radiation it emits during that process might look exactly like some of the unusual sources James Webb is cataloging. A third proposal involves a new type of stellar system, extremely dense clusters of stars, so tightly packed that they mimic some properties of active black holes without actually containing one. These hypothetical objects have been called dark star clusters or hypercompact stellar systems. The conditions needed to form them may have existed in the early universe, when gas densities and cooling rates were different from today. None of these explanations are confirmed. All of them represent genuine scientific proposals published in peer-reviewed literature. The fact that multiple competing frameworks are needed to explain a single class of James Webb observations tells you that the objects themselves are genuinely novel. The universe may contain a category of structure that formed only in early cosmic conditions and has no modern analog. Every previous revolution in observational astronomy produced surprises like this, objects that fit no prior category and eventually forced the expansion of the classification system. James Webb appears to be doing the same, and the sheer number of adjustments accumulating in response to its findings is beginning to strain the framework that was supposed to hold all of them. When a scientific model encounters unexpected observations, the first response is always to look for adjustments. Tweak a parameter here, add a physical process there, expand the uncertainty ranges in a calculation. Models are not meant to be rigid, they are meant to be refined. That is how science works, and it is healthy. The trouble comes when the adjustments pile up faster than they can be tested, when each new observation requires a new patch, and when the patches begin to contradict each other. Cosmology is approaching that situation. Since James Webb's first data releases, the list of required adjustments to the Lambda cold dark matter model has grown steadily. Star formation efficiency in early halos needs to be higher than originally modeled. Supernova feedback needs to be less effective in early galaxies than simulations assumed. Dark matter halo growth needs to be faster at high redshift. Chemical enrichment processes need to run on compressed timescales. Black hole seeding mechanisms need to be more efficient. Galaxy quenching needs to operate faster. Each of these adjustments, taken individually, is defensible. Uncertainties exist in every component of the model, and refinements are expected. But taken together, they all push in the same direction. They all require the early universe to have been more efficient, faster, and more organized than the standard model predicted. When every patch leans the same way, it raises the question of whether the underlying model itself is missing something fundamental, rather than simply needing calibration. Several prominent cosmologists have made this argument explicitly in published papers and public statements. The adjustments needed to reconcile James Webb's observations with the standard model may be collectively implausible. They require too many independent processes to all simultaneously run at their most extreme settings at the same early time. The probability of all those extremes coinciding begins to strain credibility. An analogy exists in the history of planetary astronomy. Before Copernicus, astronomers using the Earth-centered model of the solar system had to add increasingly complex adjustments called epicycles to make their predictions match observations. The system worked, technically, but required elaborate and growing machinery to maintain. When Copernicus placed the sun at the center, most of the epicycles became unnecessary. the model became simpler and more predictive simultaneously. Some researchers are asking whether cosmology is in an epicycle moment, whether the accumulating patches to lambda cold dark matter are doing what the epicycles did, maintaining a framework past the point where simpler revision would be more honest. The standard model is not about to be discarded. It has too many confirmed successes across too many independent lines of evidence. But the patches are real, and the discomfort in the community is real. James Webb is not yet providing enough data to replace the standard model. It is providing enough data to make the model increasingly uncomfortable to defend in its unmodified form. And the discomfort runs deeper than the model itself. It reaches into the simulations that were supposed to predict what James Webb would find, simulations that have now been compared directly against its observations. And the results of that comparison are something the researchers running those simulations were not expecting. Modern cosmological simulations are extraordinary achievements. Projects like Illustris, Eagle, and Simba run on some of the most powerful supercomputers on Earth. They start with initial conditions derived from observations of the cosmic microwave background, apply the known laws of physics, and evolve a virtual universe forward in time. They track dark matter, gas, star formation, black hole growth, and feedback processes across billions of simulated years. These simulations successfully reproduce many features of the observed universe: galaxy morphologies, the distribution of galaxy masses in the modern universe, the large-scale cosmic web of filaments and voids, the relationship between black hole mass and galaxy mass. For decades, this success was taken as confirmation that the underlying physics was correct and the initial conditions were well understood. James Webb has revealed where the simulations break down. When researchers compare the populations of massive galaxies that James Webb finds at high redshift against what the simulations predict should be there, the simulations fall consistently short. They do not produce enough massive galaxies in the first few 100 million years. The galaxies they do produce at those early times are less massive, less structured, and less chemically enriched than what James Webb measures. The discrepancy is not a matter of fine-tuning. In some mass ranges and redshift windows, the simulations underpredict the observed galaxy counts by factors of 10 to 100. Researchers running these simulations have responded by adjusting their input parameters, lower the efficiency of supernova feedback, allow star formation to proceed at higher rates in early halos, change the initial mass function of early stars to favor more massive objects. These adjustments can bring the simulations closer to the James Webb observations, but they come at a cost. The adjusted simulations then produce other features of the universe that do not match what we observe in the nearby universe as well as the unadjusted versions did. A simulation calibrated to match James Webb's early universe produces too many massive galaxies in the modern universe. A simulation calibrated to match the modern universe underpredicts what James Webb sees in the early universe. The tension runs through the simulations, just as it runs through the analytical models. Some simulation teams have begun exploring entirely different physical ingredients, adding interactions between dark matter particles that the standard cold dark matter model does not include, modifying the initial power spectrum of density fluctuations, including new forms of early dark energy that boosted structure formation in the first billion years and then faded away. These additions can help, but they introduce new parameters that must be constrained, and no single set of additions cleanly resolves everything. The leading simulation projects have published honest acknowledgements of their limitations in matching James Webb's data. These are not obscure fringe papers. They are statements from the groups running the most sophisticated cosmological simulations in existence, saying directly that the observed early universe does not match what their models produce. That honesty is scientifically admirable. It is also a signal that something genuine is missing from the physics the simulations are built on. And the something that may be missing, a component of the universe that operated intensely in its earliest phase and then diminished, carries a name that physicists have been debating for years without resolution. Dark energy is the name given to whatever is causing the universe's expansion to accelerate. It was discovered in 1998 through observations of distant supernovae. Galaxies are not just moving apart, they are moving apart faster and faster over time. Something is driving that acceleration, and it carries enough energy density to dominate the universe's total energy budget. Roughly 68% of the universe's total energy is dark energy. We have no confirmed physical understanding of what it is. In the Standard Model, dark energy is treated as a cosmological constant, a fixed energy density of empty space that stays the same everywhere and at all times. It exists today, it existed 1 billion years ago, and it existed in the first moments after the Big Bang. Constant, unchanging. But what if dark energy was not constant? What if it was stronger in the early universe and has since weakened? This possibility is called early dark energy, and it has received serious attention from the cosmological community specifically because it might explain some of what James Webb is finding. If dark energy was more powerful in the first few 100 million years, it would have affected the rate at which structure grew, depending on how it interacted with the matter and radiation of the early universe. It could potentially have accelerated the formation of dense structures, providing conditions more favorable to rapid galaxy and star formation. Early dark energy is also being invoked in connection with a different crisis, one that predates James Webb but has been sharpened by it: the Hubble tension. When cosmologists measure the current rate of the universe's expansion, called the Hubble constant, using two independent methods, they get two different answers. The first method uses the cosmic microwave background, the afterglow of the Big Bang, to infer the expansion rate from first principles. The second method uses distance measurements to nearby galaxies, calibrated through a chain of known distance indicators called the cosmic distance ladder. Both methods are careful, well-calibrated, and extensively peer-reviewed. They disagree by roughly 8 to 9%. That gap is too large to be measurement error. Something physical is causing it. Early dark energy, if it existed in the young universe and has since diminished, would change the distance scales derived from the cosmic microwave background in a way that could bring the two measurements into agreement. This makes it attractive as an explanation for two separate problems simultaneously. James Webb has contributed to this tension directly by measuring distances to early galaxies with greater precision than previous instruments, and by finding structures at distances that test the calibration of the cosmic distance ladder. James Webb's data provides independent checks on the expansion rate at various cosmic epochs. So far, those checks have not resolved the tension. In some analyses, they have made it slightly more acute. Early dark energy remains a theoretical proposal. It has not been confirmed. Multiple variations of the idea exist, and they make different specific predictions that future observations can test. Several upcoming telescope projects have early dark energy constraints as explicit science goals. What is confirmed is that something in the universe's energy content, physics, or initial conditions is generating discrepancies that the Standard Model cannot resolve. James Webb made those discrepancies concrete and measurable. And the next chapter takes the sharpest of those discrepancies and examines what it means not just for cosmology, but for the story of the specific galaxy we call home. The Hubble tension is the most precisely defined crisis in modern cosmology. Two numbers, both carefully measured, both claiming to describe the same thing: the rate at which the universe is expanding today. They disagree. The disagreement is small in absolute terms, but enormous in implications. Because these are the most precisely measured numbers in cosmology, built on decades of careful work, and they should be the same. They are not. The first number comes from analyzing the cosmic microwave background, the faint radiation that fills all of space uniformly, the afterglow of the Big Bang's heat. Satellite missions have mapped this radiation with extraordinary detail. By fitting the standard cosmological model to the patterns in that map, researchers derive a prediction for the current expansion rate. The number they get sits around 67 kilometers per second per megaparsec. This means that for every 3.25 million light-years of distance, space is expanding at 67 kilometers per second. The second number comes from measuring distances to galaxies in the nearby universe using a chain of calibrated distance markers. Variable stars called Cepheids pulse in brightness at rates tied to their luminosity, allowing distance measurements. Those Cepheid distances calibrate the brightness of Type 1a supernovae, which then serve as distance markers across much larger scales. Following this chain outward, researchers derive an expansion rate sitting around 73 kilometers per second per megaparsec, 67 versus 73. That difference, across the most carefully measured quantities in cosmology, implies one of three things. Either one or both of the measurement methods has an unidentified systematic error, or the standard cosmological model, which is used to interpret the cosmic microwave background measurement, is missing something, or there is genuinely new physics operating in the universe that neither measurement is capturing. James Webb was partly motivated by the hope of resolving this tension. Better distance measurements, enabled by James Webb's resolution and infrared sensitivity, could either confirm the local measurement or reveal systematic errors in the Cepheid distance ladder. Early James Webb analyses of Cepheid calibrated distance measurements have largely confirmed the higher local value, rather than pulling it down toward the cosmic microwave background prediction. The tension persists. Some analyses using James Webb data have examined alternative distance indicators, objects called tip-of-the-red giant branch stars, which provide independent checks on the Cepheid calibration. Those checks have returned values closer to the Cepheid result than to the cosmic microwave background result, adding to the evidence that the local measurement is robust. If both measurements are correct, the standard cosmological model must be incomplete. An expansion rate that changes between the early universe and today at a level beyond what the standard model allows would require new physics, new energy components, or modifications to general relativity itself. All three possibilities are being actively studied. The Hubble tension, alone, would be one of the most significant open problems in physics. Combined with everything James Webb is finding about the early universe, it forms part of a coherent picture of a cosmos that our best models describe imperfectly. And the implications of that imperfection reach inward to the story of how the particular galaxy we live in came to exist, and what that story might look like if we had to write it again from scratch. The Milky Way is not a generic galaxy. It is a grand spiral, roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars, arranged in elegant spiral arms around a central bar and bulge. It has a supermassive black hole at its center. It has a history of mergers, star formation bursts, and periods of relative quiet. It is, by many measures, a typical large spiral galaxy, and its origin story, the sequence of events that built it from a collection of gas clouds into the structure we inhabit today, has been reconstructed in impressive detail using modern observations and simulations. That reconstruction is now under review. The standard picture of the Milky Way's formation involves gradual hierarchical assembly. Small proto-galactic clouds merged in the first few billion years. Several significant merger events, including the ancient collision with a galaxy called Gaia Enceladus Sausage, roughly 8 to 10 billion years ago, added mass and scrambled the orbits of existing stars. Star formation proceeded through multiple episodes. The disk formed and stabilized, the spiral structure developed, and the whole process unfolded over 10 billion years of incremental building. If the early universe was running galaxy formation at the accelerated rates James Webb is revealing, then the Milky Way's own earliest history may have been far more violent and compressed than this picture suggests. The proto-galactic clouds that eventually merged into our galaxy may themselves have formed at extraordinary speeds and been enriched with heavy elements on timescales that the standard hierarchical model does not accommodate. Observations of the Milky Way's oldest stars support a revised picture in some ways. The most ancient stars in the galaxy's halo, some of them over 13 billion years old, are chemically primitive, containing very few heavy elements. This is consistent with forming early, before much chemical enrichment had occurred. But some ancient stars in the Milky Way's bulge, the dense central region, are old and more chemically enriched than the halo stars, suggesting the inner galaxy assembled and chemically evolved faster than the outer galaxy. This inside-out formation picture, where the central regions of a galaxy build and enrich first while the outer disk assembles more slowly, is broadly consistent with what James Webb finds in early galaxies. Central starbursts, rapid enrichment, early quenching of the innermost regions, followed by ongoing disk formation in the outer parts. If early galaxies universally formed their cores in violent, compressed bursts and then assembled their disks more gradually, the Milky Way's own central bulge may contain a record of conditions in the early universe that we have not yet fully decoded. Stars in the bulge that formed in the first billion years carry in their chemical compositions the fingerprints of whatever processes were running at extreme speeds in the early cosmos. The Milky Way is not separate from the James Webb discoveries. It is a survivor from that era. Its oldest stars lived through whatever the early universe was doing, and studying them carefully may eventually let us read the early universe's history from the inside, from the stars orbiting our own galactic center, which is a profound and disorienting thought. What comes next in this story is even more disorienting, because some of the structures James Webb is finding push the formation window so far back that they approach, and in some analyses appear to cross a boundary that should mark the absolute earliest point at which any galaxy could begin to form. There is a hard limit on how early a galaxy can form. It is set by the cosmic dark ages. After the Big Bang, the universe spent roughly 400,000 years as a glowing plasma, too hot for neutral atoms to exist. When it cooled enough for atoms to form, it went dark. The first stars and galaxies then had to wait for gas to cool and concentrate enough to collapse. The earliest theoretical window for the first star formation sits at roughly 100 to 200 million years after the Big Bang. Before that, the conditions were simply too hot and too smooth for stars to ignite. Any galaxy requires stars. Stars require a minimum formation time after the Big Bang, so there is a flaw, a hard earliest possible date for any galaxy's existence. James Webb has found galaxies being pushed closer and closer to that flaw. The current record holders for confirmed galaxy distances sit at redshifts, placing them within 200 to 300 million years after the Big Bang. The spectroscopic confirmations are solid. The redshifts are real. At those distances, these galaxies are already showing signs of structure, star formation, and in some cases, chemical enrichment. At 300 million years after the Big Bang, to show chemical enrichment, a galaxy would need to have begun forming stars within the first 100 to 200 million years. That is right at the theoretical floor. A galaxy enriching its gas right at the edge of the earliest possible star formation window means its first stars formed almost as soon as physics allowed. Some candidates in James Webb's photometric catalogues, objects with distance estimates based on their colors rather than confirmed spectra, sit at even higher redshifts. A handful of candidates have estimated distances placing them at only 100 to 150 million years after the Big Bang. If confirmed spectroscopically, those objects would sit within or at the floor itself, so early that explaining their existence requires stars forming almost instantaneously after the cosmic dark ages ended, with no delay at all. Spectroscopic confirmation of those extreme candidates is pending. James Webb's ongoing observing campaigns include targets at the highest photometric redshifts as priority objects. Astronomers are watching to see whether the confirmed distance record continues to be pushed back. If galaxies are confirmed at 100 to 150 million years after the Big Bang with significant stellar populations, the implications are extraordinary. It would mean the cosmic dark ages were either shorter than modeled, or structure formation began somehow even within the dark ages through mechanisms not currently understood. It would compress every timeline discussed in this script even further. The universe may have wasted no time at all. The moment physics permitted structure to form, structure formed, rapidly, massively, as if the early universe had been primed and ready, waiting only for the temperature to drop below a critical threshold before exploding into galaxies with a speed that leaves our models standing still. How we find out whether that picture is correct, and what it would mean if it is, leads to the next and most consequential chapter in this story. One about the specific observations that astronomers are lining up to take next, and the single dataset that could either confirm the crisis or begin to explain it. James Webb has been operating for roughly 3 years. Its lifetime is expected to extend to at least 20 years based on fuel reserves. The discoveries of its first years represent the opening of a new window, not its full view. What is being planned for its coming observing seasons represents some of the most strategically targeted science in astronomy's history. Several specific observational programs stand out as potentially transformative. The first is the systematic spectroscopic confirmation of photometric redshift candidates. James Webb's imaging surveys have identified hundreds of candidate galaxies at extreme distances based on their colors. Only a fraction have been spectroscopically confirmed. Confirmation campaigns are underway to take spectra of the highest priority candidates, particularly those sitting at the greatest estimated distances. If the current record, galaxies at 200 to 300 million years after the Big Bang, gets pushed back to 100 million years, the implications for the standard timeline become inescapable. The second priority is direct observation of population 3 stars. The theoretical first generation of stars, the pure hydrogen and helium giants that seeded the first chemical enrichment, has never been directly detected. James Webb has the sensitivity to potentially see their signatures, either through spectral features in the light of extremely distant galaxies dominated by that first stellar generation, or through gravitational lensing events that amplify individual stellar sources to detectable levels. A confirmed population 3-star observation would provide the first direct view of the universe's very first stellar objects. The third campaign involves deeper study of the little red dots and other unclassified objects discussed in Chapter 25. Extended spectroscopic observations of these sources may reveal enough detail to distinguish between competing explanations. If they turn out to be a genuinely new class of object, documenting their properties thoroughly becomes the foundation for understanding whatever new physics they represent. The fourth priority is using James Webb to constrain the Hubble tension through multiple independent distance measurement methods. Several ongoing programs are using James Webb to measure distances to galaxies using techniques that bypass the Cepheid distance ladder entirely. If those measurements systematically confirm the higher local expansion rate, the case for new physics becomes significantly stronger. Alongside these James Webb programs, other facilities are being brought to bear on the same questions. The Atacama Large Millimeter Array in Chile is observing the molecular gas and dust in early galaxies to measure star formation rates independently of optical and infrared light. The Chandra X-ray Observatory is searching for X-ray signatures of early black hole activity in James Webb targets. Upcoming facilities, including the extremely large telescope under construction in Chile, will provide complementary optical and near-infrared spectroscopy, with different systematic errors, providing cross-checks on James Webb's measurements. The scientific community is converging on these questions from multiple directions simultaneously. The rate of new papers, new discoveries, and new constraints is accelerating rather than slowing. And somewhere in the data expected from the next 5 years of observation lies either the resolution of this crisis or its final, undeniable confirmation. One observation in particular carries the most weight: a single spectroscopic confirmation of a galaxy at redshift 20 or higher, corresponding to less than 180 million years after the Big Bang, with clear evidence of an already developed stellar population, would cross a threshold that no amount of model adjustment could comfortably absorb. It would be the moment the community stops debating patches and starts discussing replacements. That moment may be closer than most people outside the field realize. Everything James Webb has found points toward the same conclusion. The universe built itself faster, earlier, and more efficiently than every model, every simulation, and every theoretical framework constructed before its launch had predicted. This is confirmed, not a theory, not a controversy among fringe researchers. The leading cosmology journals, the major research institutions, the teams running the world's best simulations, have all engaged seriously with the discrepancies James Webb revealed. The adjustments required to reconcile observations with the standard model are large, systematic, and consistent in their direction. The early universe was more capable than we thought. What remains unconfirmed is why. The candidates are real. Primordial black holes seeding early galaxy formation. Dark matter behaving differently in the early universe than the cold dark matter model assumes. Early dark energy boosting structure formation before fading. Initial conditions from the Big Bang carrying more power on small scales than standard inflation models predict. Population 3 stars, accelerating chemical enrichment with unprecedented efficiency. Direct collapse black holes, providing the seeds of supermassive central engines before the first stellar generation even died. Any one of these mechanisms might partially explain the observations. Some combination of them may be required. A completely different framework, one not yet proposed, may turn out to be the actual answer. What is at stake in this scientific crisis goes far beyond academic interest. Cosmology is the framework through which humanity understands its place in the universe. The story we tell about where everything came from, how long it has existed, and what rules it has operated by is fundamental to how we understand ourselves as a species in a vast and ancient cosmos. Every previous revision of that story, from the discovery that the sun is not at the center, to the discovery that the universe is expanding, to the discovery that dark matter and dark energy dominate the universe's composition, changed not just science, but the human sense of scale and significance. James Webb is generating data that may require another revision. The early universe did not develop slowly from simple chaos into organized complexity over billions of years in the orderly way the textbooks described. Something, and we do not yet know what, drove the cosmos to organize itself with extraordinary speed in its earliest moments. Something made the universe productive, almost from the very start. If the standard model requires fundamental revision, that revision will cascade through every branch of physics and cosmology. Dark matter theory will change. Inflation theory will change. Our understanding of black hole formation will change. The history of the Milky Way will be rewritten. The origin story of every element in the periodic table will be reconsidered. James Webb is still operating. Its instruments are functioning beyond expectations. Its fuel reserves suggest decades of continued observation. Every week brings new data from the early universe. Every month brings new papers refining the picture. The reckoning is not coming. It is already underway. And we are living in the rare and extraordinary moment when a single machine, drifting silently 1 million miles from Earth, is dismantling what we thought we knew and replacing it, piece by piece, with something stranger and more magnificent. The universe is older in its achievements than we ever imagined, and we are only beginning to understand what it did in the dark before we were here to watch.